Hi, this is Mr. Barron. I want to show you how to do a titration problem that was on the 1989 A exam. And it is a problem in which you are titrating ascorbic acid, which is vitamin C. We can assume that that acid is HA. And what we do is we use hydroxide, sodium hydroxide in particular, which reacts with our acid to produce our base and waters, our conjugate base. So anyhow, here we go. The question says that we begin with a concentration. So from the information above, we have to calculate the molecular weight of ascorbic acid. That's grams per mole. So the cool thing is that they tell you the concentration of the acid, which is 0.2211 molarity, and they tell you what the volume is, which is 0.03523 liters, that you reach a point where all of the hydroxide has reacted with all of the acid. So at that point, you will have nothing but salt water, and that's what we call the equivalence point. So the math that we do is we set up 0.2211 molarity, which is the concentration of the base, and we knew it took this particular volume, the 0.03523 liters, to completely react with the acid. So the moles that we get from this calculation will tell us the moles of the hydroxide that it took to reach the equivalence point. That's the OH minus at the equivalence point. But that's also the same moles of the acid that were present in the container. Now the cool thing is we know how many grams of the acid were there. We know that is 1.3717 grams, and that we know that it's this many moles of acid that were fully reacted when you reach the equivalence point. And again, that's when all of the base is reacted with all the acid and you're left with salt water. So I divide it by the volume here, which is 0.00779 moles, and that's equal to 176.1 grams per mole. Now here's the cool thing on the AP test. They gave a point for showing your work here. They give a point for showing your work there. This was a 2-point part of the problem. This was part A, of course. Now let's talk about part B. Part B is a bit more challenging. Part B is asking for the ionization constant. Now, when I heard ionization, I thought percent ionization, and I was actually wrong. In fact, I solved this problem the very first time thinking that they were looking for percent ionization, but there was this key word in there that made me go, it's not percent ionization. It's actually the word constant, and constant is K, and if we're looking for the acid constant is Ka. So in this problem, we're looking for Ka, and that's at a particular pH. And the pH that they give you is, they tell you the pH is at 4.23, which we can do some math and very quickly figure out that the hydrogen ion concentration at this point is actually 5.89 times 10 to the negative fifth molarity. Okay, so what is Ka? The only way to figure out Ka, of course, is by writing down an equation where we know that we have at pH 4.23, we haven't fully reacted the acid, so we still have acid left. And that acid is ionizing into H plus and A minus. So the acid ionization constant is H plus, concentration of hydrogen ions, times concentration of its conjugate base, and then we've got HA. So this is the acid ionization constant. Now what we're going to do is we are going to put a box around this key piece of information. We absolutely know the concentration of H+. If we want to find Ka, we're going to have to also find out, so I already know, I'm going to put a check mark above what I know. I already know my H+. I don't know my A- yet, and I don't know my HA, so I'm going to have to do some math to figure out those two. Well, here's the cool thing about this part. To figure out the HA, I'm going to do that part here. I do know that at pH of 4.23, we used 0.02 liters of it. They tell that to you in the question because they say that 20 milliliters of sodium hydroxide have been used. So if I multiply that times the concentration, which is 0.2211 molarity, that is going to give you the moles of acid that actually reacted, which is 0.00442, and that's the moles of sodium hydroxide that reacted. Now, the cool thing is that that pH, or that many moles of sodium hydroxide have reacted, it's a 1-to-1 ratio with HA. So I also know that it's 0.00442 moles of HA that have reacted at this pH. Now what I'm going to have to do is obviously figure out the volume in that solution when we're at pH 4.23. So I'm going to take the moles, which is 0.00442, and what I know that that specifically is how much that was taken away. There's a more important question. How much did I start with in the very beginning? Well, I actually know the amount of HA that I began with in the very beginning, and that's actually from part A. I'm going to put a box around it right up here. So that's how much of the HA I began with. I poured hydroxide onto it over and over and over and over and over again until I reacted exactly 0.0442. So obviously that's how much it was taken away, so I have to take the difference between these two, which is 0.00779 minus 0.00442, and that gives me 0.00337 moles of the HA that I have present at that particular pH. Well, the problem is I need to know the concentration, so I'm going to have to take this number and then of course divide it by the total volume that was there at the time. And if you add the volume of both the titrant and what you were titrating, you have 50 milliliters of the ascorbic acid, and then you also have 20 milliliters that you poured on top of it, and that 20 milliliters got us to the pH of this particular problem. So the total volume is actually 0.07 liters, because it's 50 plus 20 milliliters then converted to liters. When you do that, that gives you your final concentration for HA, which gives us 2/3 of the way that we need to go, which is 0.0481 molarity. Now, this is a long part of the problem. So far, we've gotten a couple of the points. I'm going to keep going on this problem because remember, now I know my, oops, sorry, wrong one. I still don't know my A minus, but I do know my HA now. So now I've got to find a way to figure out what my A minus is, how much is actually there. Well, there's a cool thing that we have for this to figure it out. Let me go to another page. So now I'm going to try and figure out what the A minus is. But we have to remember something that's going on here. That'll make our life a lot easier when doing this calculation. The thing that we want to remember when doing this problem is that when you have the reaction, let's take a look at the reaction one more time. It was HA, and it was ionizing into H plus and hydroxide. Oops, sorry, and A minus, sorry. It is a conjugate base though. So now I've got HA going into H plus and A minus. And when I look at this carefully, I notice that I know exactly how many moles of A minus I actually have here. And the way I know how many moles of A minus I have here is that I know I began with 0.00442 moles of this. You may be like, well, how did you know that? Well, hey, we figured that out here. Remember the HA? To figure out the concentration of HA, I had to know how many moles of this actually were used up. So for all the moles of the HA that was used up, produce the same amount of moles of A minus that I have here. So to figure out the concentration of A minus, it's 0.00442 moles, and I know that the volume I'm working with right now is 0.07 liters. So my concentration of A minus is actually going to be 0.063 molarity. Okay, from this point on, it's a lot more simple to figure out what Ka is. Ka, of course, is going to be my hydrogen ion concentration, which I figured out earlier. My hydrogen ion concentration earlier was 5.89 times 10 to the negative fifth molarity. And then I'm going to multiply that by my A minus concentration, which I just figured out, which is 0.063 molarity. And then I'm going to divide that by my concentration that I figured out for HA, which was 0.0481. So Ka for this particular poem ends up being 7.71 times 10 to the negative fifth. And in terms of the points that were assigned, this was assigned as a point, and that was assigned as a point as well. Now, let's talk about the next part of the problem. The next part of the problem is C, where they're asking for, in part C, calculate the equilibrium constant for the reaction of the ascorbic ion A- with water. All right, so the A- that we have can react with water, that's liquid, and form HA and OH-. So if we were going to write out this wouldn't be Ka because we're producing hydroxide, it would be Kb, and it would be HA times OH- over A-. So we need to figure out Kb. Well, the cool thing is we already know Ka from up here. So Kw is equal to Ka times Kb, and Kw is a constant, which we should always know. It's on our formula sheet. It's 1 times 10 to the negative 14th. And then we know our Ka, which is 7.71 times 10 to the negative fifth. And then we're looking for Kb. So we just have to get Kb by itself. And Kb ends up being 1.3 times 10 to the negative 10. This was actually just worth 1 point. That's it. All right, now let's go to D. D is asking for us to calculate the pH at the equivalence point, and that's when we only have salt water. So since we only have salt water, of course, it's just A- and water, H2O, and since this is the conjugate base for a weak acid, what's happening is that we're producing hydroxide ions. So we're producing HA and OH-, and we are actually going to need to start plugging in some numbers here to figure this one out. The A- we actually do know in this problem, and at the equivalence point we have a different volume, but the moles of A- that we produced, let's look at the overall equation that we started with in the very beginning really quickly. Remember, in the very beginning it was HA plus the OH-, and then we were producing the A- and the water. Okay? So if we want to know the concentration we're starting with, our initial concentration here, whatever the moles of this we began with is the number of moles of A- that we produced at the equivalence point. Because remember, all we're left with is the salt water, the A- and the HOH, the water. So the moles that we began with, believe it or not, this goes all the way back to the very beginning of the problem. The moles of HA that we started with at the very beginning was 0.00779 moles. But the volume is very different, and the concentration we end up with, and I'm going to actually rewrite this equation, it's A- plus H2O liquid. It's in equilibrium with HA and OH-. And I'm going to have to take this moles and divide it by the total volume that I ended up with in the very end of the problem, which is about 85.23 milliliters, which I believe ends up being 0.08523 liters. So this is a nice table. My initial concentration for my A- is 9.14, because I'm getting that from dividing these two numbers, 9.14 times 10 to the negative second molarity. I can ignore the water, of course. These are both 0. And then as this equilibrium shifts to the right, you have a drop in concentration of this and go up by this amount for each. I don't have any coefficients, so I can leave them just x, not 2x. And then this ends up being 9.14 times 10 to the negative second molarity. This ends up being just x, and this ends up being x. So the question is asking for what's the pH of the solution. This actually requires a couple of different steps. First off, we know that Kb is equal to HA times OH-, which is this reaction right here, over A-. From the last problem that we did, which was C, we know Kb, which is 1.3 times 10 to the negative second. We actually now know A-, and I can take this to the other side over here. And A-, actually I'm just going to set this equal to A- is 9.14 times 10 to the negative second molarity minus x. And then on top, these are both x, so it's x squared. And x is actually going to be our concentration for hydrogen.